हमारा आज का टॉपिक है पीरियोडिक ट्रेंड्स, मतलब ट्रेंड्स इन फिजिकल प्रॉपर्टीज। जब हम हॉरिजॉन्टली जाते हैं, दैट मीन्स व्हेन आई गो अक्रॉस अ पीरियड, क्या होता है ये पीरियोडिक प्रॉपर्टीज का। जब हम ग्रुप में वर्टिकली ऐसे डाउन आते हैं, ग्रुप में आते हैं डाउन, तो क्या होता है हमारे ये पीरियोडिक प्रॉपर्टीज का, ये सब देखना है अभी। जैसे पहला है एटॉमिक रेडियस। एटॉमिक रेडियस अक्रॉस अ पीरियड क्या होता है, डिक्रीज होता है, क्योंकि इफेक्टिव न्यूक्लियर चार्ज Z इफेक्टिव across a period increases। ये Z इफेक्टिव इंक्रीज क्यों करता है? क्योंकि एक ही शेल में यू आर गोइंग ऑन एडिंग proton and you are going on adding electron in the same valence shell, जिसकी वजह से the nuclear force, the nuclear strength increases, which we say as effective nuclear charge। इसको क्या बोलते हैं? effective nuclear charge बोलते हैं, क्योंकि what is the nuclear charge, what is the nuclear force acting per electron in the outermost shell। तो वैसे ही एग्जाम्पल है सोडियम ग्रेटर देन मैग्नीशियम, ग्रेटर देन एल्यूमिनियम, सिलिकॉन, फॉस्फोरस। ऐसे ये तो अक्रॉस पीरियड है पहला वाला, सोडियम, मैग्नीशियम, एल्यूमिनियम, सिलिकॉन एंड फॉस्फोरस। फिर ये जो है लिथियम, सोडियम, रुबिडियम, पोटेशियम, रुबिडियम, सीजियम, ये ग्रुप में है, ग्रुप 1 एलिमेंट्स है। सो दीज ऑल थिंग्स आर देयर। तो इसके बाद क्या है, टाइप्स ऑफ एटॉमिक रेडियस एंड पीरियोडिक ट्रेंड। एटॉमिक रेडियस का प्रॉपर डेफिनेशन, ये टेक्निकल डेफिनेशन है, distance from the nucleus of an atom to the outermost electron shell। देखिए अभी क्या है कि we know that electrons का जो मतलब इलेक्ट्रॉन को पाए जाने का जो टेंडेंसी है, जो प्रोबेबिलिटी है, वो क्या है? एज इलेक्ट्रॉन क्लाउड वी कैन नॉट से दैट वी हैव अ क्लियर बाउंड्री, लेकिन वी हैव अ रीजन। सो उस रीजन, जो रीजन इन स्पेस है, ये अगर रीजन इन स्पेस है, तो ये रीजन इन स्पेस फ्रॉम द न्यूक्लियस, इसका जो डिस्टेंस है, यही एटॉमिक रेडियस हो गया। तो टाइप ऑफ एटॉमिक रेडियस क्या क्या है? इट डिपेंड्स ऑन व्हाट टाइप ऑफ एटम इट इज। पहला जो है वो है कोवैलेंट रेडियस। जब कोवैलेंट बॉन्ड फॉर्म होता है, वो कैसे होता है, बॉन्डिंग चैप्टर में देखेंगे। कोवैलेंट बॉन्ड फॉर्म होता है बाय ओवरलैप ऑफ ऑर्बिटल्स। तो it is half the distance between the nuclei of two identical atoms bonded together by a single covalent bond। तो ये जो है जैसे Cl का Cl बॉन्ड लेंथ इज 198 पिकोमीटर। यूनिट्स क्या है? पिकोमीटर्स है, एंगस्ट्रॉम्स है। लेकिन कोवैलेंट रेडियस क्या है? कोवैलेंट रेडियस ओवरलैप के बाद ये हाफ हो जाता है। तो इसका मतलब क्या है, Cl का जो भी रेडियस है, एक Cl का दूसरे Cl के साथ जब ओवरलैप करता है, तब ओवरलैप के कारण यहाँ पे देखिए, जैसे कोवैलेंट रेडियस ऑफ हाइड्रोजन एटम कैसा है, ये एक न्यूक्लियस है, ये न्यूक्लियस ऑफ वन एटम, ये न्यूक्लियस ऑफ अनदर एटम। तो ये दोनों के बीच में जो डिस्टेंस है वो कितना है? 74 पिकोमीटर। लेकिन रीजन ऑफ ओवरलैप तो आपका ये हुआ ना, तो इसका जो मिड पॉइंट है, इसका जो मिड पॉइंट है रीजन ऑफ ओवरलैप का, और एक एटम का न्यूक्लियस का जो डिस्टेंस है न्यूक्लियस से उस रीजन ऑफ ओवरलैप का मिड पॉइंट का, ये है कोवैलेंट रेडियस, एंड दैट इज ऑलमोस्ट हाफ ऑफ द डिस्टेंस बिटवीन द न्यूक्लियस। तो क्लोरीन में जैसे Cl, ये यहां से यहां तक का डिस्टेंस है, यहां से यहां तक का डिस्टेंस है 198 पिकोमीटर। तो ये हो गया ना रीजन ऑफ ओवरलैप, ये हो गया रीजन ऑफ ओवरलैप। ये रीजन ऑफ ओवरलैप में जो मिड पॉइंट है, ये रहा मिड पॉइंट, यहां से यहां तक का डिस्टेंस है हाफ ऑफ इट, दैट इज 99 पिकोमीटर। ऐसे फिर इसके बाद क्या है, ये रहा कोवैलेंट रेडियस, दिस इज कोवैलेंट रेडियस। कोवैलेंट रेडियस के बाद क्या है, मेटालिक रेडियस। जब मेटल मेटल बॉन्ड करता है, मेटल्स हैव लूजली बाउंड इलेक्ट्रॉन्स, इसीलिए इसका रेडियस काफी ज्यादा है than covalent radius, क्योंकि metallic bonds are weaker than covalent bonds। हाईलाइट करने के कारण कलर चेंज हो गया, हम देख सकते हैं। तो whatever it is, metallic bonds are weaker than the covalent bonds। ये रहा पॉइंट। Two atoms held by covalent bonds are closer to each other. क्यों? Why I have written this point? Because the covalent bonds are formed by overlap of orbitals. अब वैन डर वाल्स रेडियस क्या है? वैन डर वाल्स रेडियस काफी ज्यादा है। इट इज हाफ द डिस्टेंस बिटवीन नॉन बॉन्डेड एटम्स इन एडजेसेंट मॉलिक्यूल्स। वैन डर वाल्स इंटरैक्शन बहुत ही वीक इंटरैक्शन है, यहाँ पे रियल बॉन्डिंग तो नहीं होता है, तो यहाँ पे देयर इज नो बॉन्डिंग, रियल बॉन्डिंग नहीं है, लेकिन मॉलिक्यूल्स के बीच में जो इंटरैक्शन है, वैन डर वाल्स इंटरैक्शन, उसका जो हाफ है वो है वैन डर वाल्स रेडियस। So it is half of the internuclear distance between the two adjacent atoms of same element belonging to two nearest neighboring molecules of same substance in solid state. और हम देख सकते हैं कि कोवैलेंट रेडियस इज लेसर देन वैन डर वाल्स रेडियस। व्हाई? बिकॉज कोवैलेंट रेडियस में ओवरलैपिंग ऑफ एटॉमिक ऑर्बिटल्स होते हैं, और वैन डर वाल्स रेडियस क्या है? इट इज ऑन अकाउंट ऑफ वीक वैन डर वाल्स इंटरैक्शन। ये एक मॉलिक्यूल है, ये दूसरा मॉलिक्यूल है, दोनों में जो इंटरैक्शन है वो वैन डर वाल्स इंटरैक्शन है, और ये वैन डर वाल्स इंटरैक्शन जो है दोनों मॉलिक्यूल के सेंटर में ये जो डिस्टेंस है उसका हाफ है वैन डर वाल्स रेडियस। ये सेंटर टू सेंटर डिफरेंस, ये जो डिस्टेंस है इसका हाफ है वैन डर वाल्स रेडियस। और जब ओवरलैप ऑफ ऑर्बिटल्स होते हैं, ये सेंटर ऑफ ओवरलैप और न्यूक्लियस के बीच में जो डिस्टेंस है ये कोवैलेंट रेडियस है। So we have seen that covalent radius is less than van der Waals radius. That is the comparison. अब देखते हैं वेरिएशन ऑफ एटॉमिक रेडियस विथ एटॉमिक नंबर अक्रॉस द सेकेंड पीरियड। ये लिथियम बेरिलियम क्या हो रहा है, एटॉमिक रेडियस ना ग्रेजुअली डिक्रीज हो रहा है। लिथियम टू बेरिलियम, बोरॉन, कार्बन, नाइट्रोजन, ऑक्सीजन, फ्लोरीन नोबल गैस में जाके इंक्रीज होता है, क्योंकि वहां पे वैन डर वाल्स इंटरैक्शन है। और यहाँ पे डिक्रीज होने का मेन जो कारण है वो क्या है कि इफेक्टिव न्यूक्लियर चार्ज गोज ऑन इंक्रीजिंग। कहाँ? फ्रॉम लेफ्ट टू राइट across a period, left to right effective nuclear charge goes on increasing, इसीलिए the atomic radius decreases। क्या है? मोर प्रोटॉन्स, ग्रेटर न्यूक्लियर पुल, यही तो है ज्यादा इफेक्टिव न्यूक्लियर चार्ज। इफेक्टिव न्यूक्लियर चार्ज increases. Okay, so next, that is the reason we are seeing this trend, atomic radii of elements in second period। ये क्या होता है? ये gradual decrease we can see in the atomic radii, लेकिन यहाँ in the noble gas we are seeing an increase। Why? Because noble gas में क्या interaction है? van der Waals interaction है, इसीलिए वहां पे van der Waals radii है which is greater than the covalent radii। Now variation in a group, atomic radii group में क्या होता है? number of shells goes on increasing, जिसके कारण इफेक्टिव न्यूक्लियर चार्ज गोज ऑन डिक्रीजिंग। तो वेरिएशन इन अ ग्रुप क्या होता है? नंबर ऑफ शेल्स गोज ऑन इंक्रीजिंग फॉर विच द इफेक्टिव न्यूक्लियर चार्ज गोज ऑन डिक्रीजिंग। और ये डिक्रीज होता है तो एटॉमिक रेडियाई क्या होगा, इंक्रीज होता जाएगा. वही हम देख रहे हैं यहाँ पे. Okay, that is what is happening. See, the atomic radius is gradually it is increasing. Okay, next, down a group, that is what I said, atomic radius increases. वही reason है effective nuclear charge क्या होता है, decrease होता है, number of energy shell increase होता है, and inner electrons shield outer electron, shielding effect जो है. Now ये shielding effect क्या होता है, inner electrons they shield the outer electrons from the effective nuclear charge. और ये shielding effect S का ज्यादा है, P greater than D greater than F. S orbital is closer to the nucleus, इसलिए इसका shielding effect ज्यादा होता है. ये आउटर इलेक्ट्रॉन को न्यूक्लियर फोर्स से ज्यादा गार्ड कर पाता है. दिस इज द ओवरव्यू, क्विक समरी. ओवरव्यू बहुत जरूरी है in order to compile all. Let us see that van der Waals radii is the largest, covalent is medium, metallic is large. तो सबसे ज्यादा ग्रेटेस्ट किसका है, वैन डर वाल्स. उसके बाद किसका है, मेटालिक. उसके बाद किसका है, कोवैलेंट. ये है ऑर्डर. दिस इज द डिक्रीजिंग ऑर्डर. नाउ ionic radii will vary because cationic radii and anionic radii varies. So next we will discuss ionic radius. So what happens in ionic radius? It is defined as the effective distance from the nucleus of the ion to the point up to which it has an influence in the ionic bond. Ionic bond occurs between a cation and an anion. So what we are seeing, this is radius of a cation and this is radius of an anion. So with respect to the neutral atom, what happens, cationic radius always decreases. Why? Because cationic radius is formed by loss of electron. We can see loss of electron taking place here, loss of electron taking place here, minus electron. So for which the effective nuclear charge increases, Z effective increases, for which the atomic radii or the ionic radii decreases. So that is what we can see. The ionic radii has decreased from 186 picometer to 98 picometer in the cation. And for anion there is gain of electron. So gain of electron takes place in the same valence shell, for which the Z effective decreases, and the atomic radii, or rather I will use the term ionic radii, since it is an ion, so it is anionic radii. Anionic radii increases. Okay, so after this, when we are talking about variation of ionic radii of isoelectronic ions, isoelectronic ions means same number of electrons. So same number of electrons, we can see 10, 10, 10, everywhere same number of electrons. But what is happening to the ionic size? When I am moving from N3 minus to Al3 plus, it is gradually decreasing. Always remember, when the charge over the anion is increasing, the size of the anion is also increasing due to electron repulsion. Because when you add more than one electron, the electron repulses and the size of the ion goes on increasing. Similar is the case when the positive charge, number of the positive charge increases, power of the positive charge increases, the effective nuclear charge increases, for which the ionic radii decreases. So greater the negative charge, what happens? Greater is the electron-electron repulsion, lesser is the Z effective nuclear charge, and ionic radii increases. Greater is the power of the positive ion, the effective nuclear charge goes on increasing, for which the ionic radii decreases. Next we have ionization enthalpy. Ionization means removal of electron from an isolated gaseous atom. Why isolated gaseous atom? In its ground state, because it is free from all other interaction. So what is the minimum amount of energy required to remove the most loosely bound electron from an isolated gaseous atom? That is equal to the ionization enthalpy. Remember one thing, that ionization enthalpy is related to Z effective. Z effective, if it is less, then ionization enthalpy will also be less, because it is held to the nucleus with less force. If the effective nuclear charge is greater, then ionization enthalpy or energy required in order to remove the most loosely bound electron will also be greater, because the nuclear force is greater. So here ionization enthalpy is always positive. Why it is positive? Because energy is required. Jahan energy is required, ionization enthalpy is positive. Wherever energy is released, the energy will be negative. So, types of ionization enthalpy. First, ionization enthalpy means the energy required to remove one electron. That is first ionization enthalpy. Second ionization enthalpy means already you have got a cation, from there you are removing electron. So to remove a second electron from a unipositive ion always means you need greater amount of energy. So this should always be greater. Why? Because you are removing it from a unipositive ion which has greater effective nuclear charge. So second ionization enthalpy will be greater than the first. So ionization enthalpy 2 will be greater than ionization enthalpy 1. So is the third ionization enthalpy will be greater than the second than the first. So I can say that each successive ionization enthalpy is higher because you are removing electron from an increasingly positive ion. So gradually the effective nuclear charge goes on increasing, for which the energy required to remove an electron from the positive ion also goes on increasing and is more and more positive. So, factors on which the ionization enthalpy depend. Size of the atom. If the size of the atom is greater, then ionization enthalpy should be less. Magnitude of nuclear charge. If the magnitude of nuclear charge is greater, then ionization enthalpy should be greater, because the outer bound electron is tightly held with the nuclear force. Screening effect of the inner electron. If the screening effect is greater, then the effective nuclear charge is, that means what? If it is screening effectively, that means effective nuclear charge is decreasing. And so what is happening? The ionization enthalpy will be low. So screening effect we have already discussed. S greater than P greater than D greater than F. D and F orbitals, electrons in these orbitals have poor shielding effect or poor screening effect, for which the effective nuclear charge increases. But for S, if the screening effect is greater, that means effective nuclear charge should decrease. It is protecting the outer electron from the nuclear charge, the nuclear force. Penetration effect of the electron. S is closer to the nucleus. So here again, S greater than P, greater than D, greater than F. Electronic configuration. Of course, if it has a stable electronic configuration, then why will it lose electron? So ionization enthalpy will be very, very high. And if the electronic configuration is so that if it loses, like group 1 element, losing an electron will get noble gas configuration. In those cases, the ionization enthalpy will be less. So it depends on the electronic configuration. This is something which I have shown, variation of the first ionization enthalpy among second period elements. So we are seeing peaks and we are also seeing dips. Okay. So observation where we have seen peak. We have seen peak in beryllium, in nitrogen, in neon. Here we have seen peaks. Why? Why the first ionization enthalpy of beryllium is very, very high? Because it is completely filled. It has 2s2 electronic configuration. Nitrogen has half-filled stability. Neon has octet configuration. So all these are stable electronic configuration, for which why will it lose electron? So the ionization enthalpy is high. Now, here we can see beryllium. Beryllium has stable electronics. So sharp rise. Rises again here. Okay. And here we can see nitrogen, half-fill stability. So here we can see neon, highest noble gas, stable configuration. Why in oxygen there is a drop? Because of electron repulsion. There is a drop. Lower energy is required comparatively in order to remove. Nitrogen से कम energy is required. फिर boron में beryllium से कम energy is required. So as you move from left to right, that means across a period, atomic size decreases, nuclear charge increases, so more energy is required to remove an electron, and ionization enthalpy increases. When ionization enthalpy increases, that means the value is more positive. Why? Because energy is required. The exceptions are between beryllium and boron. We have already discussed. Between nitrogen and oxygen, already discussed. So overall, first ionization enthalpy increases across a period, but it shows dip at boron and oxygen due to subshell stability and electron repulsion. This is another thing, the variation of the first ionization enthalpy among the first group. So when you move down the group, the atomic size increases. Down the group, the Z effective goes on decreasing. So ionization enthalpy, what will happen? Ionization enthalpy will also decrease because effective nuclear charge is less. That is what is seen. Decrease in the value of ionization enthalpy. So the nuclear charge also increases, but effect of increased nuclear charge is cancelled by the increase in the atomic size and the shielding effect. Overall effect is this. This is a plot where we can see that ionization enthalpies of elements up to atomic number 60, and here we can see high rise in helium, neon, argon, krypton, xenon. Why? They are all stable configuration. Why will they lose electron? Here we can see a dip In lithium, sodium, potassium, rubidium, cesium, losing electron will give them stability. So noble gases have sharp peaks, whereas alkali metals on losing electron can attain noble gas configuration, so they have deep valleys. So these are the sharp peaks, and these are the noble gases with complete outer shell configuration, highly stable, so high ionization enthalpy, hard to remove electron. Deep valley का reason क्या है? See, again and again, in various ways the concept is being explained. In whichever way you are comfortable, do study and retain. And the entire notes is available in the description part. Click on the link and access. So these are alkali metals with a single valence electron. Losing that will get stable noble gas configuration, and so they have low ionization enthalpy. That is what is happening here. Again, the same thing, why the trend happens across the period, down the group, same thing written in a different language. Here is the summary of the entire concept. Next, moving on to electron gain enthalpy. Electron gain enthalpy is the energy released on account of gaining of electron by a neutral gaseous atom to form a negative ion. So isolated gaseous atom on gaining electron loses energy, so delta HEG means electron gain enthalpy is negative and the process is exothermic. Always remember, addition of electron means energy is released. Removal of electron means energy is required. So, if energy is absorbed, then it is endothermic. If energy is released, then it is exothermic. So, types of electron gain enthalpy. The first electron gain enthalpy. On gaining electron, energy is released. Now, second electron gain enthalpy, there will be electron-electron repulsion. And so it is always positive on account of electron-electron repulsion. Now, does it mean that the double negative ion is not formed? Yes, it is formed by if the overall energy is getting a negative value, then only. Now, trends in the electron gain enthalpy across a period, what happens? Becomes more and more negative. Why? Because atomic size decreases, Z effective increases. It is easier to add an electron, and it has a tendency to gain an electron to get to the noble gas configuration. Down a group, what happens? Down a group, the atomic size increases, for which if you try to add an electron, it is not that easy. But there is an exception. Cl has more negative electron gain enthalpy than fluorine. Coming to it. So this is the summary of the concept. Factors on which electron gain enthalpy depends. It depends on atomic size. Larger the atom, less negative is the electron gain enthalpy. Nuclear charge, if it is higher, then more negative is the electron gain enthalpy. Electronic configuration, if it is stable, why will it gain electron? But if it is a group 17, then it can gain electron in order to attain group 18 noble gas configuration. Shielding effect. More inner electrons, reduced attraction. So these are the factors. Exception what I said, Cl versus F. See, fluorine has such a small size that if you go to add an electron, there will be electron-electron repulsion, for which energetically it will get a positive value. Now, chlorine has more negative electron gain enthalpy. The reason is the atomic size is large. It has vacant d orbitals. It is easy to add an electron, for which the repulsion is less. It gives more room to addition of electron. So less repulsion, energetically favorable. and for that reason chlorine can add on electron, releasing more energy. So this is the summary of the concept. Across a period, what happens to the electron gain enthalpy? Becomes more negative. Reason is smaller size, higher Z effective nuclear pull means Z effective nuclear charge. Then down a group, what happens? Becomes less negative, larger size and more shielding. Second electron gain enthalpy is always positive due to electron-electron repulsion. Next, moving on to the concept of electronegativity. Electronegativity is the tendency of an atom to attract a shared pair of electron towards itself. So this is the difference between electron gain enthalpy and electronegativity. Electron gain enthalpy was the tendency of an isolated gaseous atom to attract, to gain an electron. But electronegativity is the tendency of a shared pair of atom to pull electron, or I'll say tendency of an atom to attract, to pull the shared pair of electron a bit more towards itself. Suppose I talk about heteroatomic molecule AB. If B has greater electronegativity, then the electron cloud will be bit more towards B than A. The electron cloud will shift. So this is known as electronegativity. Fluorine is considered to be most electronegative element. Now across a period, what happens? The Z effective goes on increasing, for which electronegativity increases. Remember, electronegativity is related to non-metallic character. So if electronegativity increases, then non-metallic character also goes on increasing. And down a group, electronegativity decreases. So I will say the metallic character goes on increasing. So factors affecting electronegativity: atomic radii. Smaller the atom, higher is electronegativity, because smaller the atom, Z effective is greater. Nuclear charge, you know this is only Z effective. Shielding effect, more inner shell reduce the effective nuclear charge. Now, hybridization, more S character is seen in sp greater than sp2 greater than sp3. This is the S character. So if I say that the hybridization is such that the S character is greater, that means electronegativity of the atom is also greater. Electropositivity is the inverse of electronegativity, and it is directly related to the metallic character. It is directly related to the tendency to lose electron and form cations. And you know that if the ionization enthalpy is low, if ionization enthalpy is low, then only electropositivity will be high. Then only metallic character will be high. And I'll say non-metallic character will be low. So trends in electropositivity: down a group, the electropositivity increases, metallic character increases because atomic size increases, effective nuclear charge goes on decreasing down a group. Next, across a period, effective nuclear charge increases, electropositivity decreases, non-metallic character increases, and metallic character decreases across a period. So, metallic character or electropositivity is directly related to tendency to lose electrons. Factors affecting electropositivity are atomic size, ionization energy, nuclear charge, and electronic configuration again. So, what is valency? Valency is the combining capacity of an element, or rather we can say the tendency or the number of electrons gained, lost, or shared in order to achieve a stable electronic configuration. You know, every atom, every element wants to attain stability, wants to attain octet or duplet configuration. This is not called actually duet, it is called a duplet. Okay, it is called a duplet like helium configuration or octet configuration. So either it can lose or gain electron. This takes place in electrovalent compounds, or it can share electrons like in covalent compounds during any bond formation. So the number of electrons lost or gained, or the number of electrons shared, that is the electrovalency and the covalency, will give you the valency of an element. Now, how to do that? If the number of valence electron is 4 or less than 4, then valency will be equal to the number of valence electron. So it is for number of valence electron 1, 2, 3 and 4. 4 agar hai to it can gain also, it can lose also. You have to see energetically which is favorable. If the number of valence electron is 1, then it is easier to lose 1 electron than to gain 7 electron in order to get octet configuration. If the number of valence electron is 2, it is easier to lose 2 electron than to gain 6 electrons in order to get octet configuration. So this is so. If valence electron is greater than 4, then the valency is 8 minus number of valence electron. Suppose 5 valence electrons are there. Then in that case, will it lose the 5 electron or will it gain 3 more electron in order to attain octet? So it is easier to gain 3 more electron. So what will be the valency? Valency will be 8 minus 5, which is equal to 3, because it can gain 3 electron in order to attain octet configuration. Likewise, we need to find the valency. For transition element, it is variable valency, and trends in valency across period. Valency first increases from 1 to 4 and then decreases from 4 to 0 by 0, because we are talking about noble gases group 18. Why it is increasing from 1 to 4? Because it loses 1 electron. Just this formula that we have seen as per this formula. Next, going on to down a group, valency remains constant. Why? Because same group means same number of valence electron. So the valency remains constant. Next, factors affecting valency. We have already discussed all the factors. So this is the summary of our discussion. Moving on to nature of oxide, we have 3 types of oxide: basic oxide, acidic oxide, not 3, 4 types, neutral oxide and amphoteric oxide. Now, oxides are compounds of elements with oxygen. Of course, combining with oxygen, the element forms oxide. If it is E, it combines with oxygen and forms, say oxygen has a valency 2, so E2 and ON, in that manner. So let us see what happens here. Basic oxide, like example, metals form basic oxide. Why? See, these basic oxides are actually reacting with water to form base. Metals form basic oxide, non-metals form acidic oxide, because on reaction with water this gives acid. Neutral oxide means what? No reaction with water. So non-metals, some non-metals, they give neutral oxides when they do not react with water. Amphoteric oxide means both metallic and non-metallic. Why? Because it reacts with acids and bases both. We can see Al2O3, aluminium oxide, ZNO, they are all amphoteric oxides and they react with NaOH also, they react with HCl as well. So trends in the nature of oxide across a period left to right. Metallic character decreases. Non-metallic character increases. So what did we see? If it is a non-metal, it forms acidic oxide. So across a period, the nature of the oxide goes from basic to amphoteric to acidic in nature. So that is what you are seeing. See, initially metallic character is greater, so basic oxide. Again basic oxide. Aluminium forms amphoteric and then the acidic nature goes on increasing. So, greater the non-metallic character, greater is the acidic nature of the oxide. And greater the metallic character, greater is the basic nature of the oxide. It forms basic oxide. Okay. Down a group again, the metallic character increases. So, what is expected? Yes, basic oxides. So, that is what we are seeing. More basic, it goes on down the group. So this is the quick summary of whatever you have seen here. Okay. Now moving on to the last leg of our discussion. Diagonal relationship in periodic table. Diagonal relationship refers to the similarity in the properties of elements that are diagonally adjacent, and it is seen in the second and third periods. So, in group 1 and 2, group 13 and 14, second and third period elements. What is happening here? These elements, they are not in the same group, but their atomic size, ionization energy, electronegativity are comparable. Okay? So, they show similar behavior. So, that is what is seen. Lithium and magnesium, see, they are in different groups. They have diagonal similarity. These are the similarities. So, beryllium and aluminium, different groups. These are the similarities. Boron and silicon, different group. These are the similarities. So, the reason behind the similarities are what? Similar atomic size. Across a period, the size decreases, but down a group the size increases. So diagonal effect will be somewhat in between. A balanced effect, similar electronegativity, again a balanced effect, similar charge to radius ratio, that is polarizing power. So similar bonding behavior. So these are the reasons behind diagonal relationship. So I hope the explanation was clear. Kindly go through each and every point. Thank you all of you. Hoping to meet in the next session. If you like my video, do like, share and subscribe.